Good morning. Today I want us to talk about magnetism. We'll discuss it and then we'll answer a question. The topic magnetism. Ish. Magnetism. Magnetism is the science of the attractive force of magnets. It's the science of the attractive force of magnets, meaning under magnetism, that is the thing we discuss. The main thing we discuss are magnets. Magnetism, the science of the attractive force of magnet. What is a magnet? A magnet is a substance that attracts magnetic materials. Any substance that is able to attract magnetic materials, then it's a magnet. Any substance that attracts magnetic materials is a magnet. And then they ask you, what is a magnetic material? Again, a magnetic material is a substance that can be attracted to a magnet. Examples of magnetic materials include iron, steel, cobalt, and nickel. Cobalt and nickel are on the periodic table. Steel is an alloy. Iron is also on the periodic table. Those are the four magnetic materials. Substances that cannot be attracted to a magnet are referred to as non-magnetic materials, e.g. glass. Non-magnetic materials, e.g. glass, plastic, human skin, soil, air. Non-magnetic materials, those that can't be attracted to a magnet. So you can give a lot of examples here. Glass, I'll just give a few. Glass, plastic, you can even put copper, aluminum. So those are non-magnetic materials. That is like an intro on magnetism. Okay. And then we have important things to discuss on magnets. These are the properties of magnets. When you are asked to describe the properties of something, they want you to like give them the what that thing does for it to be called that thing. For example, what are the properties of like a motor vehicle? It is able to carry people from one place to another within a short amount of time. What does it do? They are the properties. So magnets, what do they do? What do they have? Property number one, magnets are able to attract magnetic materials. All magnets attract magnetic materials. If it cannot attract magnetic materials, then it's not a magnet. So all magnets attract magnetic materials. All magnets attract magnetic materials. That is the first property. The second property, all magnets have opposite regions. They have two opposite regions where their magnetic force is concentrated. These regions are known as magnetic poles. All magnets have two opposite regions where their magnetic force is concentrated. These are referred to as magnetic poles, north and south. That is a property. The third property is the law of magnets. The law of magnets states that opposite poles attract each other while like poles repel each other. Opposite poles attract, like poles repel each other. That is the law of magnets. Like poles. So poles that are similar, they are going to repel. Poles that are different are going to attract. Okay, like poles repel, opposite poles attract each other. The last property, when a magnet is suspended in air, to suspend something is to like hang it somewhere where it can swing freely. So you can suspend it by tying it maybe to the ceiling or something like that. You tie it to the ceiling and then you spin it around. It will always rest with one side pointing north, the other one will always be pointing south. So if you want to like check if this is true, paint this side red and paint this side blue. you find that after you spin it, the red will still point this way, the blue again will point this way. You spin again, the same thing, the red will always point this way. So the side that points north is referred to as the North Pole. The side that points south is referred to as the South Pole. That is how we come up with the poles of a magnet. Okay, those are the properties of magnets. Okay, so now these are the three types of magnets that we have. We have the first one is a bar magnet. It's shaped like a bar of soap or something, a bar of something, that a bar magnet. The next one is a horseshoe magnet. It looks like a U, but when you turn it around, it looks like an N. When you turn it sideways, it looks like a C. So they call it the horseshoe magnet. Looks like a shoe of the horse. When a horse is moving, this is the print it leaves in the ground, that shape. The last one is a ring magnet or disc magnet. Ring magnets, the poles are kind of strange. Some of them are going to have like north here, south there. Others will cut even here, south there, north there, like that. Different kinds of poles like that. So they don't even bring it in the exam, the ring magnet, but these two they come. Those are the three types of magnets. Sorry about that. So now, magnetic field. Talk about the magnetic field. A magnetic field is a region around a magnet where the magnetic force can be experienced. So let me again draw a bar magnet here. A region around a magnet where the magnetic force can be experienced. North and south poles. Okay. All magnets, they have magnetic fields. All of them, they have magnetic fields. So take for instance this bar magnet. So there's only like one rule on magnetic fields when you are drawing magnetic fields around a magnet. Magnetic fields come from north and go to the south. They come from north and go to the south. They are represented by a line with an arrow. So the field line will come like that. If you are asked to draw the magnetic field lines from north to south, and what indicates the direction is the arrow. From north to south. From north to south. Just like that. North to south. That is how you draw a magnetic field lines on a bar magnet. That one. You can draw more than that. You can draw as long as they don't touch. They should not touch. So draw them like that. You can even add the third one, a fourth one, like that. The magnetic field lines. In terms of a horseshoe magnet, the magnetic field lines, let's say if this is north and that is south, the field lines will come from north to south. North to south. North to south. North to south. North to south, like that. Okay, now we talk about the magnetic field lines when you put two poles together. What causes the attraction and what causes the repulsion. So when you put two opposite poles like that, north south, south could have been here, north could, but it's the same thing. So north and south, if you put two opposite poles together, since magnetic field lines come from north and they go into south, they can't manage to go there to do that. No, there's a south nearby here, so they will come from this north and enter this south. They come from this north, enter that south, like that. And then some of the things they kind of can't be touching, they even do that. That is the type of magnetic field. Then we have something like that. Showing that magnetic field lines are coming from the north going to the south. After there's no space here, they start going back to that south there. After there's no space here, they start going from that north coming to the south, like that. When you put two like poles together, two norths, magnetic field lines come from north and they don't enter the north. No, they come from north also. So those are going to repel each other and you end up with that kind of magnetic field, like that. a magnetic field like that coming out of the north on both magnets, and you're going to leave a space in between. This space that is left in between where there are no magnetic field lines passing, that is referred to as the neutral point. They do ask about it in the exam. That point, it is referred to as the neutral point. This is a region where no magnetic field lines are passing and no magnetic force is experienced. If you were to place a Castile nail there, it won't be attracted to the magnet. Okay, that is the magnetic field. So if you want, you can complete these, even go and enter the south like that. We know where they are going. We are just ending them there like that. Even this one complete, even this, the same thing. When you have two like poles, two souths put together like this, magnetic field lines come from north to south. They enter a south like that. Since these are like poles, the magnetic field lines are repelling each other, so they won't be able to touch. They are also going to create a neutral point there. There, the neutral point. So arrows are very important. We should show that magnetic field lines are entering the south, because that's what I said. All magnetic field lines come from north and they go to the south. So for all these to my field lines must be entering the south like that. These are the three types of magnetic fields that we can have between two unlike poles, between north, between south. That one. Okay, moving on to something else. Magnetization. Magnetization is the process of forming a magnet. The process where you convert a magnetic material into a magnet. So you can convert those four magnetic materials I talked about earlier: iron, steel, cobalt, and nickel. Those can be converted to magnets. So that process of converting them into a magnet is what is known as magnetization. And the methods of magnetization are listed here. We have the induction method, heating and the hammering method, the stroking method, and we have the electrical method. The electrical method is the one that is used in industries to make strong magnets, very strong magnets. This one. All these others are not even used in industries. They are just almost useless, but they are important anyway in physics. So we have the induction method. Induction method is the type of magnetizing a magnetic material without it being in contact with the magnet. So when you have a magnet, this is the induction method now. When you have a magnet like this, and then you bring like a nail made of iron or steel, it will stick to the magnet like that. Okay, so induction method, I've said, is a type of magnetization. It's a method of magnetization without requiring contact. So if you wanted like to now show that there's induction here, put the canal here, it gets attracted. How come? The magnet is so far away from it? Because this magnet has magnetized this one and it has become a magnet which has also magnetized this one. So the magnet and this one, they are not in contact, but it has been magnetized. This is induction. Just sticking to my magnetic materials to a magnet, that is induction. It's the simplest method, like that. So since this is the south pole, you know that opposite pole, according to the law of magnets, opposite poles attract. So since this is the south, so the head of the nail, since it has attracted to the south, the head of the nail must be a north, then its tail is a south. The head of this nail, for it to be attracted to that south, it must be a north, then its tail south. The head of the nail, for it to be attracted to the south, must be a north, its tail south. Even if you put my nails here again, the same thing, they stick. They become magnetized by the method of induction. So this one is pretty simple. Right, since they are attracted to this north, the head of this nail is a south, meaning the tail is a north. The head of this one, for it to be attracted to that one, it's a south, its tail is a north. The head, for it to be attracted to that north, is a south, its tail is a north. This is induction. So for the heating and hammering method, you get a magnet. This is the type of magnetization where you get a magnetic material, you heat it until it is red hot, meaning you can heat it with a fire or something. Heat it until it is red hot. When it is red hot, you place it in the north to south direction. You point it north. You should know where north is, like geographically. Use a compass or something. You know where north is. You point it in the north, and then you start to vigorously hammer it, because the method is the heating and hammering. Heat it until it is red hot. Vigorously hammer it. When it cools down, it will become a magnet. That is the heating and hammering method. And finally, not finally, we have the stroking method. We have two types of stroking method. We have the single stroking method, and then we also have the double stroking method. So for the single stroking method, this method makes both of them, they make temporal magnets. Their magnets are not permanent. So let's say you get a magnetic material and get another magnet. To stroke is to touch. So you get a magnet, you are magnetizing this thing. You get a magnet and then touch the magnet along the length of the magnetic material. So it's kind of like you're doing that. You lift it. When you reach the end, you come back, you slide it across the magnet like that. That is the stroking method. You are stroking the length of the magnet. You stroke the entire length of the magnetic materials until you reach the end. You lift it well off, you bring it back to the other side again, you stroke just like that. After some time, this one will become magnetized. But how do we know which poles will be north, which poles will be south? So the end of the magnet that is used for stroking, this one, since we have the pole north, which is used for stroking, we're using a north. Where it is being lifted, there will be an opposite pole to the pole used for the stroking. So if we're using a north here, it is being lifted here, this will be a south. Opposite to that. If we were using a south, this will be a north, opposite. Yeah, that is the stroking, the single stroking method. You use a single magnet. No wonder they call it single. You're using one magnet. You stroke the length of the bar magnetic material, this thing. When you reach the end, you lift it, you bring it back here, you stroke the length, just like that. Where the magnet is being lifted will become an opposite pole to the one used for the stroking. So this will be a south, therefore that is a north. For the double stroking method, you use two magnets. You stroke the length of the magnetic material from the center going outward simultaneously at the same time. So meaning you're going to have these two as magnets. You bring them down, you stroke the length, you reach the end, you lift them, you bring them back at the center, you stroke again, just like that. Where the magnet is being lifted will become an opposite pole to the one used for the stroking. So the south is being lifted at this end will become a north. The north is being lifted at this end will become a south. And you have made a magnet. One more thing, if you wanted to make a magnet with the same poles like north, north, south, south, you use identical poles to stroke. So if you also used this one, sorry. If you also used the north here, if this one was a north, this side will be a south, that side will also be a south. Then you have created a magnet that does the same poles. In the center, that's why we're going to have two norths there inside. So now the electrical method of magnetization. This is the last one. This results in the formation of the strongest magnet. This method. So to use the electrical method to magnetize something, you first of all get a coil of insulated copper wire. You get an electric cable, something that is able to transfer electricity, and you make a coil. You wrap it around something that is round to make a coil like this. This coil is what is referred to as a solenoid. A solenoid. So you get a coil of insulated copper wire. Simply mean get a solenoid, connect it to a DC power source, to a battery, in short. A DC power source, a battery. So it's a DC power source. DC, direct current. It only comes from batteries, not from the socket in our houses. That is AC. So DC means direct current. AC means alternating current. So that one is not used to make magnets. We specifically use DC. So in the exam, they could ask you in multiple choice. They say, Which source do we use here? He said DC power source to magnetize something. So using the electrical method, get a coil of insulated copper wire, simply meaning get a solenoid, connect it to a DC power source and turn it on, in fact. And then place the magnetic material inside the solenoid. Place the magnetic material inside the solenoid. You put the material you want to turn into a magnet, place it inside, turn on the current. After a while, this magnetic material will become a magnet. That is all about the electrical method. But they do ask, what will be the poles? Which side will be north, which side will be south? So to show the direction of the magnetic field, the north and south on this magnet that will be formed, you use what is known as the right hand grip rule. You do this good thingy. You grip the solenoid. You grip the solenoid like that, round. The thumb points in the direction of the north. Then the two fingers point in the direction of the current. So when you have a solenoid like this one and that battery, current comes from the tall one, not from the short one. So current is coming from here. So you just put in the direction of the current. They always give you a power source. So you check, you see where the tall one is. That's where current is coming from. And you put my arrows. So if current is coming from that other side, then it is coming into this side like that. It makes sense. And then you even do this now. This one, since current is passing like that, and it passes behind there, and then it passes like this here. We put in the my arrows just to show, and then like that. So now let me remove this one. Let me just remove some parts there. Can't even rub now. Anyway, that you put in the my arrows to just show how current is moving into that coil. And then using the right hand grip to the one I've just told you about, grip the solenoid as if you are gripping this thing. You grip it like this. The thumb will point in the direction of the north. So since those current, you see that my arrows, they are pointing that way. So you do your fingers like that, and then you coil them like that, meaning this side is the north. This side of this is the north. That side is the south. That is how you know the poles that will be formed, the right hand grip rule. The thumb points in the direction of the north, the fingers point in the direction of the current. So grip the solenoid like that. If those arrows were going down, would have gripped it like this, and north would have been in that direction. But since they are going like that and then coiling, north is there, south is there. That is it about magnetization. Another question they do ask in the exam on the electrical method is, how can you increase the strength of the magnet formed? By increasing the number of coils, the number of turns in the coil. How many times have you coiled it around? If you coiled it around 80 times, make it 160 times, meaning you're going to also double the strength of that magnet. That is one, increasing the number of turns in the coil. The second way of increasing the strength of the magnet that is formed is by using a stronger battery. If you get a more powerful battery, you are going to increase the strength of the magnet. So if you don't want to say battery, you can say increasing the voltage, because battery produces voltage. So if you use a stronger battery, it means you have just increased the voltage. Those two. Done with magnetization. The next one to talk about is demagnetization, the opposite of magnetization. Demagnetization is the process of destroying the magnetic properties of a magnet, converting a magnet back into a magnetic material. It's like you are reversing what we were talking about, magnetization. Now the reverse is known as demagnetization. So now the methods of demagnetization include the heating method, the hammering method, the electrical method. Remember, on magnetization, we had the heating and the hammering method. Here, we just have heating alone and hammering alone as a method, not combined. So the heating method is where you heat a magnet until it is red hot and then place it in the east-west direction. like point it from where the sun rises to where it sets in that direction, and then you put it somewhere, it starts to cool. When it cools down, it will no longer be a magnet. It has become demagnetized. That is the heating method. You heat it until it is red hot, place it in the east-west direction, and leave it to cool. When it cools down, it will no longer be a magnet. The second one, the hammering method. You place your magnet in the east-west direction, vigorously hammer it, east-west, vigorously hammer it for a while. Just hammer, hammer, hammer. After some time, you find that it has become demagnetized. It's no longer a magnet. So heating, hammering. The electrical method of demagnetization will also make a solenoid again. A solenoid. So make a solenoid. You make a solenoid and connect it to an AC supply. This is the symbol for AC, not that battery looking thing. It's like an S in there, or it could be written like that, as long as there's an S somewhere like that. That is the symbol for AC power supply. So DC is used to form magnets, AC is used to destroy magnets. So now you make a solenoid, connect it to an AC power supply, turn on the current, and then withdraw the magnet slowly. It will become demagnetized. This is one of the surest ways of demagnetizing something, because these others, they can leave some magnetism in the material, but this one, it removes all magnetism from a material. It becomes just an ordinary metal. That is the electrical method of demagnetization. The only issue to remember here is connect it to an AC supply when you are destroying a magnet. When you are making a magnet, it's DC. Destroying, AC. So sometimes in multiple choice, they do bring diagrams like this, and then they ask you what happens to the magnet, and you see that there's AC. It will become demagnetized. It will lose its magnetism. Okay, done with demagnetization. The care of magnets. How can you take care of magnets to avoid them being destroyed or them damaging other property? So firstly, we talk about magnetic screening or magnetic shielding. This is the process of protecting a device from external magnetic interference, or protecting the surrounding of a device from magnetic interference. That is magnetic screening. So you protect either a device from magnetic interference coming from outside, or you protect surroundings of a device that produces magnetic fields. Yeah. So how can you shield something from magnetic interference? You place it in a soft iron ring. Soft does not mean it's soft to the touch. No, it's called soft iron because of something. I'll talk about it. So you get a ring of soft iron, place it in a magnetic field, and then in the center place a device. Let's say we have placed a phone. Those tiny phones people use nowadays with 22 buttons. You place the phone inside the ring. When magnetic field lines are coming, they will choose to pass through this piece of iron and then out like that. Same as out like that. They choose to pass through there than through air. So meaning the device has been magnetically shielded from magnetic interference. It has been protected from magnetic interference. So if this phone was producing magnetic fields also, they won't be able to cross to the outside. That is that magnetic shielding or screening. And then we talk about keepers, magnetic keepers. Magnetic keepers. Magnets, they lose their magnetism over time. So now how do you protect them from doing that? On their own, they demagnetize. That process is known as self-demagnetization. So to protect magnets from self-demagnetization, we use what is known as ion keepers or magnetic keepers. These are pieces of iron that are placed at the ends of a magnet to prevent self-demagnetization, to help the magnets retain their magnetism. Retain, not the retain for bring back, no, the retain for keep, retain. To help magnets retain their magnetism, you place pieces of iron at the ends of a magnet. So for this bar magnet, if you wanted to protect it from self-demagnetization, use an ion keeper, a round ion keeper like that, which is round. Meaning when magnetic field lines are coming, they don't come out of the pole. Yes, they do come out of the pole, but they are not passing through air. They pass through the ion and then they enter the south. Same as through here. They come from there and then they enter the south. You won't lose any magnetism when you do this. So this is a soft ion keeper. Soft ion keeper. Sometimes they do ask, how do soft ion keepers help magnets retain their magnetism? They do this by eliminating the existence of free poles. When a magnet has got free poles, like a magnet that is just in air, these field lines that are coming out, it's like they are losing magnetism. So how do you avoid them from losing magnetism? Eliminate these free poles. Put something that will enable the field lines to pass through that thing and come back in. You don't lose them like that. So soft ion keepers, they function by eliminating the existence of free poles to help magnets retain their magnetism. Retain their magnetism. That is about soft ion keepers. So if you wanted to like protect these two magnets, you don't have a ring piece of iron. You don't have a ring piece of iron. You arrange them like that, north, south, like that, and then get any ordinary bar piece of iron and place it here at the end of this, and this one, make them touch. Another one, place it there, make them touch. Those pieces of iron, they act as magnetic keepers. Magnetic field lines coming from here, they will pass through that thing and enter that south. Those that are coming from there, they will pass through that keeper and enter that south. Just like that. These two magnets have been magnetically protected from self-demagnetization by using ion keepers. Yes. Magnetic properties of iron and steel. They do ask this question, like they ask you to differentiate sometimes. Differentiate iron and steel as magnetic materials. So meaning differentiate them in terms of magnetism. So difference number one, iron is referred to as a soft magnetic material. Soft iron, remember I said I'll explain that. Iron is a soft magnetic material. Soft magnetic material. Steel is a hard magnetic material. What does that mean? Hard magnetic material. This simply means iron is easy to magnetize. It is easily magnetized, meaning it is easy to turn it into a magnet. Iron is easily magnetized. Steel is not easily magnetized. Not easily magnetized. Iron is easy to magnetize and also easy to demagnetize. Easy to magnetize, easy to demagnetize. Easily magnetized, easily demagnetized. That's what it means to be a soft magnetic material. Steel is not easily magnetized and it is not easily demagnetized. It's difficult to like to destroy its magnetic properties. Steel. Iron is easily magnetized. Steel is not easily magnetized. That is a difference. That is what it means to be soft magnetic material or hard magnetic material. Okay. Iron is used to form temporal magnets, temporary magnets. Magnets that are not permanent. Steel is used to form permanent magnets. Steel is used to form permanent magnets. Iron is also used to form what is known as electromagnets. So it forms temporary magnets. It also forms electromagnets, magnets that use electricity. Electromagnets. Iron is used to form temporary magnets and electromagnets. Steel is used to form permanent magnets. Okay. Iron is also used to make videotapes. Videotapes, those odd things they used to put into the VHR player, those deck. They used to play movies using those things long time ago. Even those like car radios, I don't know if they still use them, but nowadays it's a flash. But sometime back they used to use tuma tapes. Those audio and video tapes, they use iron in that rope that is inside. So in making video and audio tapes, this one is used for making motors, electric motors, making or manufacturing of AC and DC motors. They are used for that. Iron is also used in formation of transformers. Transformers have got pieces of iron inside them. Even electric bells are formed using iron. Electric bells are formed using iron. Those bang, 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 bang electric ones, you just turn it on and it starts ringing. They are made using iron. Steel is used in those AC and DC motors. Steel is also used in loudspeakers. Loudspeakers, they have magnets inside them. Those magnets are made using steel. So these are the different. This is how you differentiate these two as magnetic materials. But in terms of differences, you say iron is a soft magnetic material while steel is a hard magnetic material. Iron is easily magnetized while steel is not easily magnetized. Iron is easily demagnetized while steel is not easily demagnetized. Iron is used to form temporary magnets while steel is used to form permanent magnets. Iron is used to form electromagnets while steel is used to form permanent magnets. Iron is used in formation of video and audio tapes while steel is used in formation of AC and DC motors. Iron is used in formation of transformers and electric bells while steel is used in formation of loudspeakers. Okay, so now we answer a question from 2017 GCE. 2017 GCE number B7. 2017 GCE number B7. Figure B7.1 shows magnetic field lines between the poles of two magnets. So we have those two magnets. I've drawn them here. The magnetic field lines look like they are coming out of the poles, not so, and they are repelling each other like that. Question number 1 was name region R. You see that region? I talked about this one. This is the neutral region. Neutral region, the region where you don't have magnetic field lines and no magnetic force is experienced. The neutral region, a neutral point or something. Let's call it a neutral point. Instead of region, let's say point, the neutral point. Then B is, if P is a south pole, they have given us now that P is a south. If P is a south pole, what are the poles Q and T? If P is a south, this one will be a north. So Q is a north. If this one is a north, you look at the field lines, they are coming out of it. Same as here, they are coming out of it. Then S is also a north. If S is a north, then T is a south. So T is a south. That is that. On C. Explain how soft iron keepers help magnets to retain their magnetism for a longer period of time. They do this by, I talked about this, eliminating the existence of free pores. Eliminating the existence of free pores. So they are placed at the ends of a magnet and then they eliminate the existence of free pores. That is how they do it. The last one, D. State two differences between iron and steel as magnetic materials. Iron is a soft magnetic material while steel is a hard magnetic material. Iron is a soft magnetic material while steel is a hard magnetic material. So that is one difference. Iron is a soft magnetic material while steel is a hard magnetic material. That means iron is easily magnetized while steel is not easily magnetized. The second one, iron is used in the formation of temporal magnets while steel is used in the formation of permanent magnets. Iron is used in the formation of temporal magnets. Steel is used in the formation of permanent magnets. So that you can even add another one if you want. Iron is used in formation of audio and video tapes and electric bells and transformers, while steel is used in the formation of electric motors, AC or DC, used in the formation of loudspeakers, all those. And we are done with this question.